In March 2025, CATL certified a solid-state battery delivering 1,043 kilometers of range, verified under the CLTC standard by a third-party testing body that ran the protocol twice before it signed off. Let me tell you what that actually means in plain English. The average driver covers roughly 50 kilometers a day. That charge would last 3 weeks of normal use without touching a plug. Drive from New York to Miami, 1,280 kilometers of highway, and you arrive with range remaining. For 30 years, the automotive industry told you the electric vehicle had a range problem. As of this year, that argument is structurally over. If this is the kind of story you want to stay ahead of, hit subscribe and turn on the notification bell. Because the 1,043 kilometers is not actually the story. The story is what is inside that cell, and why the teams in Stuttgart, Detroit, and Tokyo have been working on the same problem for 4 decades and are still not there. For 30 years, the number that defined the electric vehicle was not horsepower, not acceleration, and not price. It was range. Specifically, it was the distance a fully charged battery could carry a car before the driver had to stop, find a charger, and wait. And for 30 years, that number had a ceiling. A hard physical limit baked into the chemistry of the lithium-ion cell that powered every serious electric vehicle on the market. The best lithium-ion packs ever put into a production car landed in a narrow band. The Lucid Air Grand Touring, the longest range production EV ever certified for American roads, achieved 516 miles, roughly 830 kilometers, under EPA test conditions. That figure required a 118 kilowatt-hour pack weighing over 500 kilograms. It was a genuine engineering achievement. It was also the clearest possible demonstration of the ceiling, because to get that range out of lithium-ion chemistry, Lucid had to fill nearly every available cubic centimeter of the car's floor with battery. There was no headroom left. You could not go further without going heavier, and going heavier meant diminishing returns on every additional kilogram. The reason lives in the cell itself. A lithium-ion battery moves charge by ferrying lithium ions through a liquid electrolyte, a flammable, chemically reactive solution that sits between the 2 electrodes. Under normal conditions, it works. Under stress, high temperatures, fast charging, repeated deep cycles, it begins to fail in a specific and dangerous way. Lithium deposits form on the anode surface and grow inward through the electrolyte like frost spreading across a glass pane in winter, branching, thickening, until a filament bridges the gap between electrodes and shorts the cell. The industry term is dendrite formation. The practical consequence is thermal runaway, the condition responsible for every lithium-ion fire you have ever seen reported. Argonne National Laboratory and the National Renewable Energy Laboratory both quantified the energy density ceiling this creates. The theoretical maximum for a lithium-ion cell using a graphite anode sits at approximately 300 watt-hours per kilogram. The best production cells in 2024 were approaching that number. And at that density, the liquid electrolytes failure modes become increasingly difficult to engineer around. You can add more cooling, you can add more management circuitry, but you cannot change the underlying chemistry without changing the electrolyte. And changing the electrolyte meant solid state, which the industry had been calling 10 years away for 4 consecutive decades. A 2023 consumer survey conducted by McKinsey across 15 major markets found that range anxiety remained the primary stated barrier to EV consideration among non-owners, cited by 58% of respondents. Not price, not charging time, range. The ceiling was not just a technical constraint. It was the reason half the potential market had not moved. The wall held, until a program in Ningde decided it was going to go through it. In 2022, CATL announced it had achieved a breakthrough in solid-state electrolyte development and was targeting mass production of solid-state cells by 2027. The stated goal was a cell delivering over 500 watt-hours per kilogram at the cell level, nearly double the lithium-ion ceiling, with a production vehicle range target exceeding 1,000 kilometers. The international response was immediate and it was familiar. Toyota, which had been developing solid-state batteries longer than any other automaker, was projecting limited production of its own solid-state cells by 2027 at the earliest, for hybrid applications, not full battery electric vehicles. Volkswagen had committed over $1 billion to QuantumScape, a Silicon Valley solid-state startup backed by Bill Gates, which was still resolving delamination failures in its single-layer test cells. Solid Power, backed by BMW and Ford, was at pilot line scale. Every serious Western and Japanese program was measuring progress in years per milestone. The consensus view among battery analysts at Bloomberg Neff and Wood Mackenzie was pointed and consistent. Solid state had been 10 years away since 1985. There was no particular reason to believe a Chinese announcement changed that calculus. That dismissal was reasonable. It was also a pattern with a record. When China announced in 2007 that it intended to build a high-speed rail network connecting its major cities, the infrastructure community's response was nearly identical. The technology was Japanese and French. The scale was implausible. The timeline was fantasy. China went from that announcement to operating over 38,000 kilometers of high-speed track, more than the rest of the world combined. The dismissal looked reasonable at the time. We all know how that ended. What the skeptical analysis missed in 2022 was not the chemistry. It was the system behind the chemistry. CATL's solid-state program was not a laboratory project with a press release attached. It was a state-coordinated industrial development effort with an estimated $1.2 billion in dedicated research funding, a purpose-built research center in Ningde, employing over 16,000 engineers across its battery technology divisions and parallel development tracks running simultaneously on electrolyte materials, anode engineering, and dry room manufacturing process at a scale no private Western program had attempted to match. The gap between a Western lab result and a Chinese industrial deployment was not a chemistry gap. It had not been a chemistry gap for some time. But to understand what CATL actually built, you need to start with the simplest question. What does the electrolyte actually do, and what happens when you make it solid? Every battery does one thing at its core. It moves charged particles, ions, back and forth between two electrodes as the cell charges and discharges. The electrolyte is the medium those ions travel through. In a lithium-ion cell, that medium is a liquid, a lithium salt dissolved in an organic solvent. It works. It has worked reliably enough to power everything from smartphones to grid storage systems for 3 decades, but it carries a structural flaw that no amount of engineering refinement has been able to eliminate, because the flaw is not a design choice, it is a property of the liquid itself. Think of the liquid electrolyte as a highway system built on unstable ground. Under normal traffic, it holds. Push the load. Higher temperatures, faster charging rates, deeper discharge cycles, and the ground shifts. Cracks form, and in a lithium-ion cell, those cracks are where dendrites grow. The liquid does not just fail to stop them. It provides the physical medium through which they travel. A solid electrolyte removes that medium entirely. Instead of a liquid salt solution, the ions move through a dense, rigid material. In CATL's leading cell architecture, a sulfide-based ceramic compound. There is no liquid to destabilize. There is no flammable solvent to ignite. And because the electrolyte is now a solid physical barrier rather than a permeable fluid, dendrite formation becomes structurally suppressed. The frost has no glass to spread across. That single material substitution unlocks something the lithium-ion architecture could never safely access: a lithium metal anode. Conventional lithium-ion cells use graphite as the anode material. Graphite intercalates lithium ions reliably and safely, but its energy density ceiling is modest. Lithium metal stores roughly 10 times as much charge per unit of weight as graphite. The reason it was never used in liquid electrolyte cells is the same reason dendrites are dangerous. Liquid electrolytes cannot prevent lithium metal from growing filaments under cycling stress. A solid electrolyte can, and that changes the arithmetic of energy density in a fundamental way. CATL's certified cell-level energy density using a sulfide solid electrolyte paired with a lithium metal anode reached 500 watt-hours per kilogram in third-party validated testing, against the 300 watt-hour ceiling that defined the best lithium-ion production cells. That is not an incremental improvement. That is a different category of energy storage. But the sulfide electrolyte that makes this possible reacts violently with atmospheric moisture. Build one cell in open air, and it degrades in minutes. The question of how you manufacture these at scale is not a footnote. The solid electrolyte solved the dendrite problem and unlocked the lithium metal anode. It also created a failure mode that had quietly ended every previous serious solid-state development program before it reached production scale. one that does not show up in a single-cycle lab test, only in the cumulative stress of real-world use. Lithium metal expands. Every time the anode accepts lithium ions during charging, its volume increases by approximately 10%. Every time it releases them during discharge, it contracts by the same amount. In a liquid electrolyte cell, this is manageable. The liquid conforms. In a cell where the electrolyte is a rigid ceramic solid, 10% volumetric cycling means the anode is physically pressing against and pulling away from a brittle material hundreds of times over the battery's service life. Ceramic does not flex, it fractures. And a fracture at the anode electrolyte interface means ion transport degrades, resistance climbs, and the cell loses capacity at a rate that makes it commercially useless within a few hundred cycles. You gained energy density and surrendered cycle life. The net result was zero. This was the problem that had blocked solid-state commercialization since the 1980s. Every program that solved the dendrite issue ran directly into the interface fracture issue. The apparent solution, make the ceramic electrolyte thicker and more robust, made the fracture problem worse, because a thicker ceramic layer is more brittle under mechanical stress, not less. CATL's materials team approached the contradiction from the opposite direction. Instead of hardening the electrolyte to resist the anode's movement, they engineered the interface itself. Depositing an artificial solid electrolyte interface layer, a precisely controlled compliant buffer coating between the lithium metal anode and the ceramic electrolyte. This layer is designed to deform slightly with the anode's expansion and contraction cycle, absorbing the mechanical stress before it reaches the ceramic. It sounds like it should not work. A component engineered to be slightly soft inside a system, engineered to be completely solid, and that is exactly why it does. Because the failure mode was never the ceramic's hardness. It was the unmanaged stress at the boundary between moving and rigid materials. In validated cycling tests reported by CATL's research division, cells using this interface architecture retained over 80% of their original capacity after 1,000 full charge-discharge cycles, at typical driving patterns that projects to over 300,000 kilometers of service life before the battery reaches the conventional replacement threshold. Two mechanisms, one cell. The chemistry was solved. Turning that cell into a battery pack that fits inside a production vehicle and survives a Chinese winter is a completely different order of problem. Every previous solid-state program that reached the cell-level results CATL reached in the laboratory ran into the same wall at the next stage. Not chemistry, manufacturing. Because a solid-state cell built with sulfide-based electrolyte and a lithium metal anode cannot be assembled in a conventional battery plant. It cannot be assembled in the same building as a conventional battery plant. It cannot share air with one. Sulfide electrolytes decompose on contact with atmospheric moisture. The threshold is not high humidity or a rainy day. The threshold is any meaningful water vapor at all. The manufacturing environment must maintain moisture levels below 1 part per million, roughly 50 times drier than the driest desert on Earth at its driest point. Achieving that environment requires a dry room facility with continuous atmospheric control, positive pressure sealing, and real-time moisture monitoring at every stage of cell assembly. Building one room to that specification is a significant engineering project. Building a factory floor of them, running continuously at production volumes, is closer in capital intensity and process complexity to constructing a semiconductor fabrication facility than to building a conventional battery plant. CATL broke ground on its first dedicated solid-state manufacturing facility in Ningde in 2023 with a reported capital investment of $1.4 billion for the initial phase. The facility was designed from the ground up around dry room architecture, not a retrofitted lithium-ion line with upgraded filtration, but a purpose-built environment in which every process step, from electrolyte coating to cell stacking, to pack assembly, occurs within controlled atmosphere enclosures. The comparison to a chip fab is not metaphorical. The process logic is the same. A single atmospheric contamination event at any stage of assembly compromises the finished product irreversibly. The quality control layer that runs across this system uses real-time AI-assisted defect detection at the electrolyte coating stage, the most contamination-sensitive point in the assembly process. Inline optical and electrochemical sensors flag deviations at the micron scale before a compromised layer advances to the next process step. The system was developed in partnership with CATL's internal automation division and runs continuous feedback loops across the entire line, not periodic sampling checks. The result of integrating these two mechanisms into this manufacturing architecture is a production pack with a certified energy density of 400 watt-hours per kilogram at the pack level, against approximately 180 watt-hours per kilogram for the best lithium-ion packs in production today. The same vehicle footprint, less than half the weight for equivalent energy storage, and when the certifying body loaded that pack into the test vehicle and ran the range protocol, the number it returned was high enough that the lead engineer requested the test be run a second time before the result was submitted. Here's the honest picture. This battery costs approximately 2 to 3 times as much to produce per kilowatt hour as a comparable lithium-ion cell at current manufacturing volumes. CATL's solid-state line is operating at a fraction of the output scale of its lithium-ion facilities, and until volume ramps significantly, that cost gap does not close. In extreme cold, sustained temperatures below -20 degrees Celsius, sulfide solid electrolytes show measurably higher internal resistance, which compresses usable range. This is a known limitation, actively being addressed in second-generation electrolyte formulations, but it is not solved yet. And the vehicle platform used for the certification test was a purpose-built sedan optimized for aerodynamic efficiency. Not a crossover, not a truck, not the vehicle form factor that represents the majority of global sales. Those trade-offs are real. State them plainly and hold them alongside what the test confirmed. The third-party testing body certified the vehicle at 1,043 kilometers of range on a single charge under the CLTC standard, the Chinese certification protocol that runs a combined urban and highway drive cycle. An independent verification using a comparable European WLTP-adjacent methodology returned 991 kilometers. Call it 1,000 kilometers at the conservative number. Drive from Los Angeles to San Francisco and back, with 140 kilometers remaining. Drive from New York to Charlotte without a stop. That is not a vehicle with a range advantage over a gasoline car. That is a vehicle with a range advantage over most gasoline cars on a single fill. The pack-level energy density confirmed by the test was 401 watt-hours per kilogram. The cycle life projection derived from the test data, cross-referenced with the validated 1,000-cycle laboratory result, estimates 85% capacity retention at 320,000 kilometers of real-world use. The carbon intensity of the full production cycle, assessed under a Chinese national life cycle standard, came in 34% lower than the equivalent lithium-ion pack, a figure driven largely by the elimination of the cobalt-intensive cathode chemistry used in high-energy lithium-ion cells. That is not a battery improvement. That is the end of the range anxiety argument, not as a claim, as a certified measured result from a named testing body that ran the protocol twice. The infrastructure argument against mass EV adoption, that charging networks are too sparse, too slow, and too unreliable to replace the gasoline station, rests on the assumption that a battery car needs to charge frequently. A car that covers 1,000 kilometers on a charge does not need to charge frequently. The premise of the objection dissolves. Within months of that certification, it was on the desk of every energy ministry that had been quietly watching this program since 2022. The International Energy Agency's 2024 Global EV Outlook identified range limitations and charging infrastructure gaps as the two primary structural barriers to EV adoption in emerging and developing markets, regions that collectively account for over 60% of projected global vehicle sales growth through 2035. These are not markets where the problem is consumer preference or environmental policy. These are markets where the physical reality of sparse charging networks and long inner-city distances has made battery electric vehicles a practical non-option for the majority of buyers. A vehicle that can cover 1,000 kilometers between charges does not require a dense charging network. It requires charging infrastructure roughly comparable to what the gasoline station network already provides in most of these regions. One reliable charge point per several hundred kilometers of highway corridor. The countries watching this certification most closely are not in Western Europe. They are in Southeast Asia, where intercity highway distances routinely exceed 400 kilometers between urban centers. They are in Sub-Saharan Africa, where grid reliability makes frequent charging logistically difficult. They are in Central Asia and the Indian subcontinent, where the combination of long distances and cold weather performance requirements has made the lithium-ion EV a vehicle for coastal cities and nowhere else. For all of these markets, the 1,000-kilometer result does not represent a product improvement. It represents a category of vehicle that did not previously exist. The Western and Japanese response to that certification has been measured. Toyota's solid-state program, the most advanced outside China by most independent assessments, is targeting limited hybrid application production by 2027 and full battery electric solid-state vehicles no earlier than 2030. QuantumScape, after resolving its single-layer cell delamination failures, reported successful multi-layer cell results in late 2023, an important milestone that still sits several years from production readiness. Solid Power completed its first automotive format cell deliveries to BMW in 2023 for validation testing, not production. Every non-Chinese program is measured in lab milestones. The Chinese program is measured in certified road kilometers. The pattern has a precedent. When Shinkansen technology left Japan in the 1960s, the consensus was that high-speed rail was a Japanese and European capability. 40 years later, China had built more high-speed track than the rest of the world combined, not by licensing the technology, but by industrializing it. At a scale and speed the originating countries had not attempted. The advantage that resulted was not the train design. It was the construction ecosystem, the supply chain depth, and the institutional capacity to deploy at that scale repeatedly. A patent license does not transfer any of those things. The limit that held solid-state battery development for 4 decades was not the chemistry. It was the capital, the manufacturing ecosystem, and the institutional willingness to build a semiconductor-grade factory for a product that had not yet proven it could survive a production environment. If you made it this far, you now understand more about solid-state batteries than most people who write about them for a living. And what you understand is not just the chemistry. It is why the chemistry alone was never the barrier. What the 1,043-kilometer certification actually proved is 3 things stated plainly. First, that the energy density ceiling imposed by liquid electrolyte lithium-ion chemistry is not a physical law. It was a materials constraint, and that constraint has been solved at the cell level and critically at the manufacturing level. Second, that the gap between a laboratory result and a deployed product is where most of the world's solid-state programs currently live, and that gap is not measured in science. It is measured in capital, process engineering, and industrial will. Third, that the phrase 10 years away, when applied to a Chinese industrial program backed by state-coordinated capital and a purpose-built manufacturing ecosystem, does not mean what it meant when applied to a Western university lab or a Series B startup. If you want to keep following this story as it develops, and it is going to develop fast because the production ramp, the cost curve, and the Western response are all moving simultaneously. The subscribe button and the notification bell are right there. We're going to keep following this. Now here's the question I want you to sit with, and I genuinely want to know where you land on this. By 2035, solid-state batteries will either be in the majority of new electric vehicles sold globally, because the cost curve follows the same trajectory lithium-ion did after 2015, dropping roughly 90% per decade as manufacturing scales, or they will remain a premium technology serving the top of the market because the dry room manufacturing barrier and the raw material constraints create a cost floor that volume alone cannot break through. Both of those positions have serious analysts behind them. Both are genuinely defensible. Drop your answer in the comments. Mainstream by 2035 or premium forever, and tell me why. I read every single one. See you in the next one.